Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Okay, today lecture we're going to continue talking about issue regarding conductor as shown here. Okay, so we have discussed the issue regarding conductivity, and then we have also show method to determine resistance using field theory approach. Okay, and we know the resistance that appear in this situation is not due to the reason because we are placing a device known as resistor. So the resistance going to appear due to the usage of material known as conductor. Okay, so the resistance is due to the usage of conductor material in our maybe design or in our circuit. So therefore, that's done. So what I'm going to do and continue today in our lecture, we're going to talk about conductor under static condition. That should be our objective, conductor under static condition. Okay, for those who have textbook and want to refer to the textbook, which topic actually deal with this issue that I'm explaining today, so please refer to section 5.4, okay, and then page wise to be page number 184. Please do that. So you will find information that will be very helpful. Maybe the way I'm explaining not very clear. I'm sorry about that. You need more information. So please refer to this particular references. Yeah? Okay. So now, what is the issue that we want to talk about today? So what is conductor? So conductor, we know that it's just a medium. So I'm going to draw my conductor to be a medium. Okay, so that should be always option number one. Remember, when we talk about medium in this subject, we must have first component will be what medium that we are talking about. So since the title of the discussion is conductor, so we must use medium known as conductor, and then we know for conductor there must be a special value to represent that medium, and we have shown it, and it's known as conductivity. Okay, that should be the first thing that we should mention. So the second parameter that important in the discussion should be the field. So from the wording under static now, so meaning that we want to investigate what happened to the medium when we expose to static field, and the field that we are mentioned here, we want to utilize here should be electrostatic. So I'm going to put E applied. Okay, because the title suggests that under static, meaning that the static here should be electrostatic. Okay, so conductor exposed to electrostatic field. So that's what the issue now. What happened to the conductor when we expose to static field? Under static here indicate electrostatic. That should be the second parameter needed in the discussions, correct? Okay, so that's that. So we want to look into the particles. Okay, so what happened to the charged particle in this particular medium? So that should be option number 3. Remember, we need charged particle, charged particles. Okay, so therefore that should be option number 3. And we know charge here can be represented with general representation, which is volume charge density. Okay, so we want to know what happened to this volume charge that exists in the conductor when we expose to the electrostatic field. And please remember the difference between this configuration compared to our previous model of discussion. In previous model of discussion, we assume the conductor is part of a circuit, meaning that whenever we expose the conductor to the electric field, we're going to create current because the current can flow due to the is part of circuit, meaning that it has a means to flow. But in this particular discussion, the conductor is floating. It's not connected to any circuit. So meaning that there's no way for the charge to move as what happened in our previous discussion where the charge moving, because there's a path that the electron can flow. But in this case, the conductor is stated to be isolated or floating in the space or in the air. So what will happen to our volume charge when we expose to the electrostatic field? So that's the issue now. Okay, in order to discuss about the issue, I'm going to draw, okay, because we are investigating rho v, correct? So my outcome, so my expected result, I'm going to put here my expected result. Expected results. So result of what? Result of how does the charge behave with the E applied. Therefore, I'm going to draw a graph. Okay. Since we are investigating charge, so the vertical axis should represent my charge distribution, correct? And then the horizontal axis must represent time. Okay, so let's say 0 here. Okay, so assume when t smaller than 0. So meaning that we are assuming when time is less than 0, E applied is equal to 0, meaning that the conductor is not being exposed to any electrostatic field. Okay, and then where rho v, which is the volume charge, is said to be equal to rho v naught, meaning that there's a value. So therefore, on the graph, let's indicate that to be here. So let's say rho v naught. So meaning that the charge, the volume charge is equal to rho v naught, which is a number here, meaning that there's appear to be charge in the center part of this particular medium when the medium is not exposed to any electrostatic field. So then, what happened then when we expose the medium to electrostatic field? So therefore, I must derive an equation that having the parameter rho v and time, because I need to plot the graph, and the graph must be based on the equation that contain the parameter of rho v and time. So we need to develop that equation. From that equation, we're going to plot the graph. So that's what we're going to do. So how we develop the equation? So we want to develop the equation of rho v with respect to time. So using, atau ya, from the continuity current equation. Remember the equation that we developed together when we talk about the model of current equation, which equation is known as continuity current equation. We developed 3 model current equation, equation 1, 2, and 3, where equation 1 is known as convection current density. Equation 2 is how we relate the current to the current density. Good. Equation number 3. So we state that the divergence of J is equal to negative d rho v over dt. Okay, that should be our starting point. And then from this equation, we can observe there's rho v. Yes, that's what we want to be, because that should be the vertical axis of our graph. And there's a t. Yes, that should be also needed because we want to plot with respect to t. But what we can see, there's a j term here. There's no information about j on the graph. So j need to be converted into rho v or time. How do we do it? Okay, so and then we've been informed when we talk about conductor, okay, J is equal to sigma E. Remember that equation? Okay, we call this equation as conduction current density. So why I can use this equation in my discussion? Because what medium that we are dealing now in our discussion? Yes, good conductor. So due to that reason, I can use this equation in my substitution. Because why? Conductor contains parameter as sigma, and then the sigma is needed, so we're going to put it here. So now the equation that we have, the new equation that we develop is sigma divergence of E equal to negative d rho v over dt. So, have we successfully converted the equation only consists of rho v and t? The answer is no, because why? We can still see this term is in terms of electric field, which we cannot plot on this graph. So we need to again convert that using which equation now? Good. So we can also know divergence of D equal to what? Rho v. Remember that equation? And then we assume, okay, divergence, so we can take out the epsilon now, epsilon naught, divergence of E equal to rho v. Anyone recall what name of this equation? Good. We call this one as Maxwell equation number 1, and the medium of interest here is conductor. Where conductor, the permittivity can be assumed to be epsilon naught. Okay, so it's quite similar to the value of permittivity of free space. That's a unique behavior of conductor. Okay, then we can substitute in our equation. So finally, okay, what we obtain here after the second substitution, what we going to have? Sigma, okay, what else? Over epsilon naught multiplied with rho v, do you agree on that? Equal to minus d rho v over dt. Do we agree? Okay, we substitute this term with rho v over epsilon naught. So I'm going to combine the constant sigma epsilon naught, and then I'm going to have. So alhamdulillah, we managed to convert from general equation of continuity current equation into a final equation that only contains rho v and time. Okay, because sigma and epsilon naught are constant. So what we end here, rho v and time. So we have to solve this problem now in order to plot the graph here. So what we need to do to solve, okay, solve. So I have to split first. So I'm going to have what here? Okay, I'm going to solve now using simple mathematics, splitting now. Better use black ink now. So first sigma over epsilon naught, that should be, and then I'm going to shift the time to the left. So let's put negative here, should be equal to d rho v over rho v. Can we do that? So we are separating into two components now. So the rho v on the right and then the time on the left. So what I have to do then, I have to integrate. So when I integrate both sides, I'm going to have now, so remember 1 over x dx, I'm going to end with ln rho v. That should be the integration on the right hand side. Should be equal to, integration of this one should be equal what? Good, negative sigma over epsilon naught t. Okay, because we integrate respect to time. Since there's no limit here, so I have to add constant. I'm going to put plus ln rho v naught. Why? Because at time t equal to 0, my rho v is equal to rho v naught. So that should be my constant I'm going to place when the t equal to 0. Okay? When t equal to 0, ln rho v should be equal to ln rho v naught as what we stated in this suggestion earlier. Okay, so then when I convert this equation, so finally my rho v will be equal to rho v naught exponential minus sigma over epsilon naught t. Okay, alhamdulillah, we managed to find the solution of rho v against time. Okay, so now this should be my results that I need to plot on the graph of what? Rho v against time. Okay, let's plot the graph now. Then we know that for conductor, okay, so what we're going to say now, for conductor, what should be the value of sigma? From the discussion that we did prove in my previous lecture, for conductor, sigma value always be large or small. For good conductor, that's good, very large. Okay, so if I do that, when the sigma value is very large, so meaning you have a very large number here minus t, then if I plot the graph now, meaning that I now apply the E greater than 0. So meaning that I'm now putting what? So let's assume now E applied not equal to 0 for the case t is greater than 0. Okay, so we are exposing the conductor now with our electric field. So now I'm going to use this particular solution to plot the graph. So when I increase the t slightly, we can see that initially the rho v is at this position. When the sigma is very large, t is having some number, you can see that the rho v straight away will become 0. Okay, that should be the case. Why is becoming like this? Again, it's based on the solution of the equation that we obtained. From this solution is indicating that as t increase slightly, since the sigma value is very large for conductor, the value of rho v naught, the rho v, which initially is rho v naught, will becoming 0. So the better the conductor, the higher the sigma, the faster the rho v is becoming 0. Okay, so therefore the first properties of conductor when exposed to electric field is this. Okay, now I'm going to put forward properties now. So properties. So properties of what? Properties of conductor under static condition. Okay, what should be the first thing that we observe just now? Good. So the first thing that we observe that rho v is equal to 0. So we're saying that inside a conductor, there's going to be no charged particle. initially when the charged particle having value rho v naught, as we expose the conductor to electrostatic field, those rho v naught is gone. Okay, it's not there anymore because rho v is equal to 0. Therefore, we always state when a conductor exposed to electrostatic field, we are assuming there is no volume charge. Okay, that should be the thing that we're going to state. So then what going to happen now? So we go back to our diagram now. So we know that rho v is becoming 0. Okay, so now the charge initially appear to be inside the conductor is no more. So what happened to those charge? Actually, those charge now is being shifted to the surface of the structure because the charge can only move within that conductor medium. Because why? The sigma allow the charge to move. But beyond that conductor, the charge can't move. So meaning that the charge being converted, the volume charge being converted to become surface charge. So what happened here, on the surface where the E applied is penetrating the medium, is going to be filled with negative rho s. Okay, on the surface where the E field coming out from the conductor, that particular region will be filled with positive charge, positive rho s. So that's what is actually happening to the volume charge, meaning the volume charge now being changed into surface charges. Because logically, this charge cannot move beyond the conductor medium because the region here and down here is non-conductor. So meaning that the charge can't move. Okay, so the charge can only stay in the region that at the border of the conductor medium. So what is happening here? We are creating rho s. So rho s charges, okay, being created from what? From rho v that we stated earlier. Okay, that's what we are saying now. So rho s charges being created from the rho v, and the way that the charge distribution is being arranged is such that depending on the E applied. Since the E applied from bottom to top, so the bottom surface going to be filled with negative charge, and the upper surface going to be filled with positive charge. Let's say the E applied from left to right, you will see that in the left surface here going to be filled with negative charge, and the right surface here going to be filled with the positive charge. So the way of the configuration, the distribution of polarity of surface charge will depend on the E applied. Okay, you know that the rho v now been converted into surface, yet the polarity where the positive and negative of the surface charge still are depending on the E applied, how the E applied being induced to our conductor medium. Okay, that should be the second logical properties. Yeah? So meaning that we're going to have surface charge on the boundary of conductor medium. Okay, so why? This surface charge come from where? From the volume charge. Okay, so what happened then when you have a surface charge? Okay, when you have surface charge, so this region is filled with positive rho s, and this lower region is filled with negative rho s. That configuration going to introduce new electric field. And this electric field, remember, always move from positive to negative. So this red field is due to the existence of rho s, and we call this as E induced. Okay, is a vector. And you can see the direction of E induced is from positive charge to negative charge of the surface charge that been created due from the volume charge. And what you can see inside the conductor, okay, E net, meaning that the resultant E. So the resultant E actually is equal to E applied plus E induced, correct? Because we can see there are two different electric fields appear to be in the conductor medium. The E applied, the original field that we directed to the conductor, and then the charge, volume charge becoming surface charge now producing new field, we call it E induced. So now in the region of conductor, there are two electric field, electrostatic applied, electrostatic induced. So therefore, the E net should be the sum of these two fields. And since the direction of our E induced is opposite to E applied, for conductor, the net E must always be equal to 0. That should be the third properties of conductor under static condition, meaning the resultant E inside the conductor is 0. So number 4, what we're going to say, we know that grad V equal to negative E. Remember that equation? Okay, and then since E is equal to 0, okay, therefore we have equipotential surface. Okay, meaning that the potential on the conductor always remain constant. Okay, so meaning that it's norm, remember when we apply voltage at this position, and then at this position also having the same voltage value. So same as what we are proving here. When the E applied, introduced to the conductor, this conductor having constant potential. Okay, so because the E net inside the conductor is 0. So why we are saying that? Because we know from gradient formula, remember the equation that we link between the V and the E, since the E becoming 0, the slope of the graph of V also becoming 0. So from our graph that we plot, if gradient 0 meaning it's flat, meaning that the potential of that particular graph V is constant. So that's what we are saying, the structure having equal potential surface. So that the conclusion, what happened when conductor material being exposed to electrostatic field. Four main characteristics as indicated here. So please go through these properties because we're going to use a lot when we talk about in future problem, because in our future problem, the problem more related to practical world which utilize material in the problem, whereby in our previous problem that we solve, material is always assumed to be free space. But if we are dealing with conductor material, we can see now from these discussions that these four properties must be considered when we want to solve real engineering problem. Okay, so therefore, what we have done here, we have completed this part already. Okay, what is it? So we have completed conductor under static conditions. Okay, that's what we, alhamdulillah. So please go through. So I'm going to do what now? I'm going to continue with this other part now, conductor free space boundary condition. Okay, that should be our next logical step to discuss. So I'm going to put either a title now boundary conditions. Electrostatic boundary condition. Okay, boundary condition. Okay, so what is the issue now? So let's say now you have a boundary. And for the sake of discussion, let's say our boundary appear to be flat like this. Smooth, so let's assume something simple here, flat and smooth. So assuming the upper region is known as medium number 1, and the lower region is having number 2. So from this simple diagram, we know that we are dealing with a boundary that's separating two different medium. The upper region consists of medium number 1, and the lower region consists of medium number 2. So they are different medium now. Okay. So what we're going to talk now, we're going to talk about the field. How actually the electric field propagate from one medium to the other. Okay, so that's the issue now. So to talk about this issue, we can take example of when that we can observe light when it propagate from, let's say, water to air. Okay, that's a good scenario that we can, that good analogy that we can use in this discussion. So let's say medium number 2 is water, medium number 1 is air, and our field is the light. So what happened to the light? Good. So the direction of the light being changed. Okay, and why I can take light as an example? Because light is an electromagnetic field. And we know that electromagnetic field consists of electric field as well as magnetic field. So from that analogy, we can state here the direction of electrostatic field when it propagates from medium number 2 into medium number 1 also going to be changed. So that's what going to be the condition we're going to state now. So this should be the normal to the boundary. Okay, this should be representing my field in medium number 2. So it's electric field. I'm going to denote as E2. Similar to the behavior of the light when it's entering the air, the direction of the light going to be changed. I'm going to make it to be changed for electric field as well. So this should be E number 1. Okay, so we know that the electric field, in terms of behavior, is going to obey this pattern. Change of direction when it moves from one medium to another medium. Okay, so this is the case. So now, so what we have to do now, we have to create equation at the boundary. So what we need to know, what we have to do now, we have to develop equation that need to relate E1 and E2. So we have to develop that equation. How that E1 and E2 are related based on this diagram. Okay, so where this particular relationship being focused at the boundary. So we're going to develop at the boundary. Where? Here. Because at that point only the E1 and E2 actually interact with each other. You cannot assume the mathematics we develop here to be located at this position, because at this position is only consists of E1, correct? There's no E2. Similarly, I cannot consider that this position, because at this position, the only field that appear to be only E2. E2. So my discussion now is focused at this particular point where the E1 is actually meeting with E2. So meaning this is the equation that we want to develop. Yeah. What happened to that particular relationships? Okay. So since every time if we assume the medium change, okay, let's say now if I change my medium 1 to be something else, and then we can see the effect of changing the medium, the direction of E1 also will change. So in order to develop equation that is not relate easily, meaning that when you change medium, the direction will change, so it's dynamic, so it's not fixed. It's very cumbersome and tedious. So what we need to do here in order to simplify the process of developing this equation, we're going to see there are two conditions always constant with respect to the boundary. Regardless what happened to the boundary, the normal component always normal to the boundary, correct? Normal meaning that the angle of that field making to the boundary always 90 degrees, always remain 90 degrees. And second, that the parallel field that we call it tangential component to the boundary always remain the same. Regardless what you change the position of the boundary, the normal always remain normal. Why? The angle always remain 90 degrees. Similarly, the parallel component always angle 0 degree to the boundary. So it's much easier if we purposely split the E1 into two components which contains the normal as well as the tangential. Because the normal always remain normal to the boundary, the tangential always remain tangential to the boundary. So let's make it easier like this. Okay, let's see if I split the E1 into two components. Okay, I'm going to say to myself, let's say make it equal to E1N. Very sorry about that. So this meaning that normal, and this component equal to E1T. Okay. T stand for tangential or parallel to the boundary. So can I change the equation E1 to become E1N plus E1T? Is it allowed in terms of mathematics? I think it's allowed because we are splitting the field into two components. One component normal to the boundary, another component parallel to the boundary. In terms of mathematical term, they are valid. Okay, similarly, if I do that to the E2 normal, E2, let's say E2 now consists of E2N, which is normal to the boundary, and also this component should be E2T. Therefore, I can say to myself, E2 also can be rearranged to be represented with equation E2N plus E2T. Okay, so this is what we are doing. We just creating another form of equation representing our E1 and E2, and the new equation contain two components with respect to the boundary, which are one component normal to the boundary, another component is parallel to the boundary. We call it tangential. Okay. From there, what we're going to do, we're going to create an equation based on the normal component here going to be related to the normal component here. So this is what we're going to focus based on each individual component. So this is going to be our first equation. We call it boundary equation number 1. Okay, boundary condition number 1. We call it boundary condition number 1. So which is only focused on the normal component of the field. Okay, that's done. That should be our first equation that relating E1 and E2, but only focusing on the normal part of the equation. Then if we focus on the second term of t to the second term of t, so we're going to have the second boundary condition equation. Okay, we call it boundary condition equation number 2, and this focus on the tangential component. So what we have then, when we talk about electrostatic boundary condition, going to be in terms of two different equations. One will be based on the normal component, another one will be based on the tangential component. Okay, so that's what we have to do, because it's easier to relate normal to normal because the direction fixed. Both component always normal to the boundary, correct? And also it's much easier to relate this parallel component to this parallel component because still the direction is fixed. Okay, wherever you change the boundary condition, the parallel always parallel, the normal always parallel. Sorry, the normal always normal. Okay, so that should be the idea. So now I'm going to focus on the first one, the boundary condition number 1. So let's do that now. Boundary condition number 1, which is focused on normal component. So we're going to ignore the horizontal component at this stage. We're just only focusing on the normal. So let's redraw that in terms of diagram. So the boundary still remain the same. Okay, that should be our boundary. Similar to the above, nothing changed. The upper region we're going to denote as region number 1. The lower region we're going to label to be region number 2. So our normal component, so it's going to be appearing like this. So this should be my E to N, okay, correct? Similar to the one shown up here. And this is going to be my E1N. Okay, so that should be 1N. So that's what we're going to create now, equation that relating these two components. We're totally ignoring the other components. So this particular diagram is much easier for us to develop equation. Yeah? So that's what we're going to do. So how are we going to start? Okay, to develop E1N with the E2N now. Okay, so to do this in electromagnetic world, we must always go back to the fundamental equation, and those fundamental equations are known as Maxwell equations. How many Maxwell equations have we seen so far in electrostatic field scenario? That's good. There are 2 Maxwell equations. So therefore, I'm going to use one of those Maxwell equations in this analysis. So which one you think that I'm going to use now? Good. So I'm going to use Gauss Law. So using Maxwell equation number 1. Okay. So what does it say? Divergence of D equal to rho V. So remember that equation in point form or in integral form. We're going to say that D dot ds is equal to what? Anyone remember this equation? Yes, Gauss Law equation, Q enclosed. They are the same. This is known as point form. This is known as integral form. They are the same equation. So I can use either one. So in this case, I'm going to use this particular term, which we are more familiar. And we have done a lot of examples using Gauss Law. Remember this equation in Gauss Law? Okay, so let's do it now. Okay, when I want to use Gauss Law, I have to see my problem now. So in this case, since we have a charge here, so let's assume on the boundary, we're going to place a surface charge. Okay, so this is what I'm going to do now. Because why? Because from this equation, I see there's a Q charge. So therefore, due to that reason, now I'm assuming on this boundary, there is surface charge? Assume rho S exists. Okay, somehow when in the problem the rho S not exist, we're going to place at the end of this equation rho S equal to 0. Okay, but since we want to develop general equation of the normal component, we're going to place a charge here and we assume the charge to be surface charge, because why? From the Maxwell equation number 1 of Gauss Law, we can see there's a charge there. So therefore, that's the reason why I'm doing this. But this assumption will not affect our result. Because why? If in our result, there's no charge appear in the problem, let's say there's no surface charge appear in our actual problem, what we can do, in the final equation that we going to develop here, we're going to substitute rho S equal to 0. Okay, so therefore it doesn't matter. We just create a general equation now. Okay, that's done. So now, since we are using Gauss law, what is important now? Yes, we have to build a Gaussian profile, correct? So now, what should be our Gaussian profile here? Okay, so I can see in this particular scenario, we have infinite surface charge structure. Okay, infinite surface charge structure. So I can use cylindrical coordinate by placing my Gaussian to be like this. So this is my Gaussian that I'm going to build. Okay, so meaning the Gaussian going to be a cylindrical structure having, let's say, the area here, okay, I'm going to assume to be, let's say, S, and the height here, I'm going to assume to be H. Okay, so there you are. So now, what I'm going to do, I'm going to relate the Gauss law equation to my structure. So what happened? Okay, I want to, so how many different surfaces I can see from my cylinder? Okay, let's label them. So this surface number 1, the top area. The side area, surface number 2. And the bottom area, surface number 3. So how many terms I can expand from this equation? Good, 3. So it should be surface number 1, d dot ds1. Okay, that's will refer to surface 1 of our cylinder plus surface number 2, d dot ds2. Okay, finally surface number 3, d dot ds3. Okay, we're still focusing on the left-hand side. I'm still ignoring the right-hand side in this discussion. I'm just focusing on the left now. Yeah? So we're going to do the right-hand side later on. Okay, so now I'm going to see. Okay, my intention now, I just want to have the final C of the equation that comprising my E1n and E2n, correct? So meaning that the area of interest going to be area number 1 and area number 3. How about area number 2? Area number 2 will include the parallel component field, correct? Because that should be the field that coming out from our surface. But do we want to talk about that field here? Because we are focusing on normal only. So we don't want it to be discussed. So what we're going to do then in order to eliminate that side of mathematics? Good. So we're going to assume now. Assume that the H here tend to 0. So meaning that the H value is very, very small. So due to that argument now we can state that the surface number 2 mathematics will becoming 0 because the height is negligible. Yeah, too small. So therefore, that particular side of the term, ds2, going to be assumed to be ignored. Because why? In this model, we just focusing on the normal component, ignoring the tangential component of the boundary field. Okay, so let's do the mathematics now after ignoring the area number 2. Okay, what we're going to end now, or we're going to have here, okay, let's look at the side now. Okay, so side number 1 here, what we can see? We can see E1n direction-wise to be upward. Do we agree? Going up? Yes, because we know that the D and E actually the same. Remember, we are saying what? We are saying D. I'm going to write note here. Note D equal to epsilon naught E. Do we agree on that? So meaning the direction of D and E actually the same. So if the E in this direction, the D must also be in this direction. So this mathematics involving D. So therefore the direction of D here is from this, meaning showing upward. Okay, and also the DS, as what we are being informed, always coming out from the Gaussian. Therefore, what we can see from this particular situation of region number 1, the direction vector of field and surface, they are the same. So the dot product will give us positive value. So what we're going to have now, D1n multiplied with S. The S is the total area after integration. Okay, good. So let's see. So number 2, we don't have to bother. Let's go for number 3 now. The area at the bottom of the cylinder. So we can see in this particular region number 3, the field must obeying the E direction, which is still upward. Okay, the D now also is upward. But the direction of DS3 is coming out from the cylinder, which is downward. Now you can see the direction of both vector D and DS, they are opposite. So when you do dot product, it's going to be n with negative. And then what we're going to have, D to n, and also since the area up here and bottom here are the same, so multiply with S. Okay, that should be the solution of the Gauss law based on the left-hand side of the equation. Okay, so let's proceed now to the right-hand side, equal to. So when charge now, so we are focusing on the charge. The charge is considered to be where? Yes, as the statement here, enclosed. The charge must be the one that appear to be in the Gaussian. So what are the charge to be inside the Gaussian from the diagram? Yes, should be this charge, correct? The volume charge. Okay, so we are going to take sample now, dq. Okay, so I'm going to take now sample dq. So what type of charge that we are dealing now? Good, surface charge. So what should be the model mathematic of surface charge? Rho s multiplied with ds. Okay, so when I solve the mathematics, so what should be the integration of the area here where the charge is actually being evaluated? We can see the area is the same as the top area and also is the same as the bottom area. So therefore, the final integration going to be n with rho s multiplied with s. Okay, so our final normal component equation that we can conclude, okay, d1n minus d2n will be equal to rho s. So remember, so this should be our boundary equation number 1. So boundary condition number 1, or we call it normal component. Okay, so that should be the equation that must remember. So I'm going to use this equation in my next discussion, so please remember. So that should be based on our normal component. So whenever we talk about normal component, so that should be our selected equation. So logically, what we should do then? Good. So I'm going to continue with developing another equation, but focusing on the tangential component. So let's do that now. Yeah. Okay. So let's do it now. So I'm going to go for boundary condition number 2. So this focus on tangential component. Okay, so that should be our objective. Okay, so let's draw the diagram now. So the diagram going to be the boundary. That should be our boundary. And then region number 1 is up here. Region number 2 is down here. Right? Okay, and then how about the field profile? Okay, the field going to be the one here. I'm going to make it, okay, these directions. We call it to be what here? E1t, remember? So vector. And the bottom direction is going to be E2t. Okay, so how we relate these two fields together? So we need to develop equation in order to relate E1t with the E2t. Okay, when this field propagate into region number 1, how this equation actually are relating to each other. So that's what we are intended to do. Again, we're going to follow the step that we used in our previous model development. Okay, so I'm sure by now you can see the logic now. We start with what? Good. Using Maxwell equation number 2. Anyone remember what should be the equation Maxwell number 2 here? Okay, I'm sure you could remember, or you lost already because we've been learning too many equations. Okay, let me help you here. So the equation appear to be like this. E dot dl equal to what? 0. Remember the equation that we developed together when we talked about potential difference? We did example, then we have conclusion as such. So this is the conclusion that we have, where we are saying that the result potential difference is independent of path. The only important is the initial position and the ending position. So that should be the starting point where we develop this equation. Okay, so that should be the equation that we referred. Now, since the mathematics here involving length, and the length is completely closed, do we agree on that? So I'm going to develop structure now. So my structure now should be the blue structure now. Okay, and you can see it's completely closed. I'm going to indicate the corner here as number 1, number 2, number 3, and number 4. Okay, I'm going to give dimension now. So let's say I'm going to give the dimension, the width as L, and the height here as H. Yeah, so therefore that should be my structure of length that I'm going to refer to when I want to solve this mathematics. Okay, so let's do that now. So I'm going to relate the equation with the structure now. So we can see I'm going to do mathematic wise from 1 to 2 E dot dl plus where to where then? Good, 2 to 3 E dot dl. Do we need to continue? Yes. 3 to 4 E dot dl, and finally we're going to have 4 to 1 again E dot dl, because the mathematics that we use up here is a closed loop integration starting from 1 ending at 1. Okay, that's done. Now, so from this particular simple diagram, we just want to focus on the issue of field pertaining the tangential. We don't want the normal component to be appear in our end solution. So what we need to do in order to eliminate the normal component? Good. So we're going to repeat the same approach as before. We're going to assume what here? Yes, the h here tend to be equal to 0. So we are ignoring that particular side of integration. So I'm going to state now, due to that assumption, this term from 2 to 3 going to end with 0. And the term from 3 to 1, sorry, this should be 4. I'm very sorry. It maybe it's late at night already. So now it's about 1 o'clock in the morning. So I'm a bit tired. So 4 to 1 also going to end with 0. Okay, so therefore, so now our life is become easier. We only focusing on the tangential. So let's do that now. So what we're going to have now, okay, from 1 to 2, let's look at the segment of 1 to 2. From 1 to 2, what we can see, the E1T is there, correct? And then the integration is moving from where to where? 1 to 2. Therefore, the direction of DL also same as the direction of E. Do we agree on that? So when they have the same direction, the dot product, is it going to be positive or negative? Positive. So I'm going to have E1T. What should be the product of the integration? Good, L. That should be the solution of integrating from point 1 to point 2. Okay, and then we're going to focus from 3 to 4 now. Okay, so we can see from this mathematics, we are integrating from 3 to 4. The direction is from 3 to 4, yet the field in this segment still remain at 4 to 3. Therefore, DL direction vector and E direction vector are opposite. So if I do the dot product, is it going to end with positive or negative sign? Good, negative. So negative E to T. Okay, this direction is just scalar now, and the result of this integration is equal to 0. So can we simplify the mathematics? So finally, what we're going to have now, we're going to see that E1T is equal to E2T. So that should be the standard equation of boundary condition number 2 that contain the tangential component, meaning that when the field in this form, the field just penetrate to the other region without anything change. Because, so that's what is happening. When you want the energy to transfer from one medium to another medium, we need to configure the field orientation to be parallel to the boundary. By doing that, we can see from the mathematics, the field can move to the other region without any loss. So that's how people design antenna when they want to absorb energy from the air to the conductor. So the profile of the field must be tangential to the boundary. Okay, this is the example that they use in the design. Okay, so we have already N2 equation. Boundary condition number 1. Okay, and boundary condition number 2. Okay, so this is the equation that you're going to see a lot on the discussion. Okay, so but what we are doing in this particular part of the discussion, we are actually dealing with what we call here conductor free space. Okay, but yet in our discussion in this particular issue, we are saying medium number 1 is just number 1, medium number 2 just number 2. But actually we want to relate now conductor free space. So now let's say we're going to make it more specific by saying conductor free space boundary condition. So we're going to relate it to be more specific now, we're going to relate with the medium now. Okay, so let's see now. We're going to say now, number one, change into what is known as free space. Okay. Number two now, we're going to assume to be our conductor. Okay, so let's recall for the first one, boundary condition number one. Okay, boundary condition number one, or we call it normal component. So what should be the equation that we have? D1n minus D2n is equal to 0. That's general equation that we developed together. Agreed? Okay, so now let's relate to medium now. What's special about conductor? And can you recall what's special about conductor? The properties of conductor under field. Anything that you can recall? Good. So let's recall this condition that we developed together. So let's focus on item number 3. What does it say? Okay. Statement number 3 state that the E in the conductor will equal to 0. Correct? Okay, so let's relate that to our equation that we are developing now. Okay, so medium of conductor is which number? Number 2. So we are saying now for conductor, D2 must equal to 0. Okay, so the final equation for conductor free space, that D1n is equal to rho s. Okay, that should be our equation that we need to have. Focus on the normal component. Why? D1n minus D2n equal to 0 based on general medium of boundary condition that we proposed earlier. Now we're going to relate that general medium to our specific medium now, where we are assuming medium number 2 is made of conductor. And from our previous discussion that we see, in a conductor, the net E is equal to 0, remember? So therefore, that will be the same here. The electric field in the medium of conductor will become 0. So the final equation that we have here, okay, should be equal D1n equal to rho s. So that should be our first equation for conductor free space boundary condition. Okay, so now we are converting from general case or medium into specific focus on conductor free space. And D1n, the field that appear to be in the free space. Okay, so that one. Okay, so that's done. So let's now focus on the second equation. Boundary condition number 2, as what we see above here, tangential component. What we say here, E1t is equal to E2t, correct? And again, using the properties that I mentioned up here, inside the conductor, the E is equal to 0. Therefore, this term must also be equal to 0, correct? Since the E2t equal to 0, E1t must also be equal to 0. Do we agree on that? Good. So now we are saying E1t equal to E2t equal to 0. So what we are saying now, we are saying at the boundary of conductor free space, there is no tangential component field. The only field that appear to be always the normal component. So let's draw now a boundary now. So let's say this is our boundary, general shape now. Okay, so let's say medium number 2 on the left, medium number 1 on the right. Okay, number 2 made of conductor, medium number 1 is made of free space. And let's say for the sake of argument, on the surface here, they consist of surface charge rho s. So meaning that there's a lot of charge appear to be at the boundary of conductor free space, and that's indicated as rho s, surface charge density. How you draw the field at this particular situation? Okay, the field must only be appear in the medium known as free space, correct? Good. And the field must always be normal to the boundary. So whenever you see the field going to be normal, so normal. And here, if I draw the field, it's going to be normal. If I draw the field here, it's going to be normal. So that should be the configuration of the field at the boundary between conductor free space. And remember, the way that we denote the field D, the D is electric field density in the free space region, should be equal to rho s A normal. The A normal is unit vector normal to the boundary, and the magnitude of the field based on equation number 1 must be equal to surface charge density. So that should be the special behavior that always be for the case when you are dealing with boundary of conductor free space. Okay, you can just use these properties without proving it, just saying that at the boundary of conductor free space, the field only appear to be in the region of free space, and the direction of the field must always be normal to the boundary, and the magnitude of the field D is equal to the surface charge density that appear to be on the boundary. Okay, so alhamdulillah, with that, I'm going to show back to you our planned learning material in electrostatic field. So we have done this part. So meaning that this segment of conductor have been completed, alhamdulillah. Yeah? So I'm going to show example regarding this issue in my next tutorial video. So we're going to take problem from handout number, I presume number 7, which I haven't uploaded yet. Inshallah, I'm going to upload the handout as soon as possible. And then inshallah, in my next lecture, I'm going to talk about the issue shown below here. So I'm not going to talk about dielectric here because the video is long enough already, and most of you need time to absorb the idea that I'm suggesting here. So hope that my explanation is helpful for you to understand now medium play a very important role in electrical problem. You can see the equation we developed based on free space need to be changed according to the medium that we are dealing with. Okay, thank you very much for your attention. Hope you find something benefit from my explanation. With that, I would like to say thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.